Welcome to This Explainer. If you're the kind of focused learner who just loves knowing exactly how things tick, well, you are definitely in the right place. Today, we're popping the hood on the ultimate, hyper-efficient biological engine that keeps us alive, the cardiovascular system. We're talking about a system that flawlessly transports oxygen, nutrients, hormones, and waste products. It regulates your body temperature, balances your pH, and even acts as a superhighway for your immune system. But to truly appreciate the sheer brute power of this setup, we really have to look at the raw numbers.
5. That is the astonishing amount of blood in liters that this biological engine pumps every single minute. And get this, that's when you're completely at rest. I mean, just imagine 5 massive liter-sized bottles of fluid being forcefully circulated through thousands of miles of microscopic piping inside your body every 60 seconds without you even having to think about it. It's an absolutely incredible feat of biological engineering.
So here is our blueprint for today. We're going to cover the body's ultimate engine, following the blood trail, the spark and pump, pipes, pressure, and control, and finally, when the engine stalls. Let's get right into it.
Part 1. The body's ultimate engine, specifically its structure and layers.
Nestled right there between your lungs and the mediastinum, just slightly left of your midline, sits the engine block itself, the heart. If we move from the outside in, we see it's wrapped in this really tough protective outer sac called the pericardium. Next in line is the epicardium. But the absolutely crucial layer here is the third one, the myocardium. This is the thick muscle powerhouse of the heart. It's the layer that actually contracts and does all the heavy lifting. Finally, on the inside, we have the endocardium, which is this incredibly smooth inner lining that keeps all that blood flowing seamlessly through the chambers. Now think of the heart not as just one single pump, but actually 2 separate pumps working totally side by side. The right side is essentially the collection facility for your used blood. It takes in deoxygenated blood returning from the body and gently pumps it right next door over to the lungs. The left side, on the other hand, receives that freshly oxygenated blood from the lungs and has to forcefully eject it all the way out to the very tips of your toes and the top of your brain. Because of that massive workload, the left ventricle has the thickest wall by far and operates under the highest pressure.
Moving on to Part 2, following the blood trail, looking at the dual circuit. We actually have 2 distinct, continuous loops working perfectly in tandem here. The pulmonary circuit deals strictly with the deoxygenated blood, routing it straight to the lungs to pick up fresh oxygen and drop off carbon dioxide. Meanwhile, the systemic circuit handles all that oxygenated, nutrient-rich blood, driving it outward to nourish the entire rest of the body. Let's actually follow a single drop of blood on its journey. Okay, so used blood from the body enters the right atrium via the vena cava. It drops to the tricuspid valve down into the right ventricle, and then it's shoved out through the pulmonary valve into the pulmonary artery, headed straight for the lungs. Once it picks up that fresh oxygen, it races back via the pulmonary veins into the left atrium, drops past the mitral or bicuspid valve into that incredibly powerful left ventricle. Finally, it just bursts through the aortic valve into the aorta, out to the rest of the body. Passing through these 4 mechanical doors ensures our blood only ever moves in one direction, forward.
Part 3. The spark and pump, focusing on the cardiac cycle and conduction.
It's all about perfect balance. Notice how a single 0.8-second cycle, which is what we call the cardiac cycle at a resting heart rate of roughly 75 beats per minute, requires absolute precision. Systole is that tight, powerful squeeze where the ventricles contract and blood is forcibly ejected out. Diastole is the essential resting period right after, where the ventricles relax, allowing those chambers to completely fill back up. Squeeze, refill. Systole, diastole.
You know that famous Lub-Dub heartbeat you hear through a stethoscope? Well, fun fact, it's actually not the sound of the muscle squeezing at all. It's the auditory echo of those mechanical doors we just talked about forcefully slamming shut. The first sound, the lub, or S1, is your atrioventricular valves, the tricuspid and mitral valves, snapping closed. The dub, or S2, is the crisp sound of your semilunar valves, the pulmonary and aortic valves, snapping shut right behind the ejected blood to keep it from washing back in. But what actually tells the muscle to squeeze in the first place? Your heart has its very own built-in electrical grid. It kicks off at the SA node in the right atrium, which acts as your natural pacemaker, firing away at roughly 60 to 100 beats per minute. That signal then travels to the AV node, which does something crucial. It delays the impulse for just a fraction of a second so the atria can finish fully emptying into the ventricles. After that, the signal races down the bundle of His and spreads rapidly outward through the Purkinje fibers, causing the ventricles to contract. Whenever you look at an ECG reading, those famous P, QRS, and T waves, they're simply the visual graphs of this electrical charging and discharging, known as depolarization and repolarization, spreading across the muscle.
Bringing the pump and the spark together gives us our ultimate metric, cardiac output. You calculate this by taking your stroke volume, which is the amount of blood pumped out per beat, roughly 70 milliliters, and multiplying it by your heart rate. By instantly adjusting the preload, which is how much the heart stretches before pumping, the afterload, the resistance it pushes against, or just the sheer strength of the squeeze itself, your body perfectly calculates and adjusts its necessary output. It keeps that baseline of roughly 5 liters per minute going and ramps it up the very second you start exercising.
Which brings us to part 4, pipes, pressure, and control, the vascular network. Leaving the heart, blood literally crashes into the thick, muscular walls of the arteries. They're heavily reinforced to handle immense pressure and regulate flow resistance. From there, the blood flows down into the capillaries, and these vessels are so incredibly tiny, they're literally only 1 cell thick. This is where oxygen and nutrients are hand-delivered directly to your tissues. Finally, the low-pressure venules and veins gently carry the used blood back up to the heart. Because the pressure is so incredibly low by this point, veins actually have thin walls and built-in valves to prevent the blood from just falling backward due to gravity. Just like any closed plumbing system, whether it's in your house or a whole city grid, you have to maintain a precise pressure to keep fluid moving without bursting the pipes. Your blood pressure is a product of your cardiac output multiplied by the peripheral resistance of your blood vessels. As we all probably know from our routine doctor visits, normal resting levels are hovering right around 120/80 millimeters of mercury. To completely avoid catastrophic pressure drops or spikes, we rely on 3 highly sophisticated internal regulators. The autonomic nervous system uses built-in sensors called baroreceptors to detect instant pressure changes. We've also got a hormonal cascade called RAS, which can quickly tighten up blood vessels to boost pressure. And finally, our kidneys, which directly control the overall fluid volume of the body. Working together, they are constantly tweaking the dials in the background to keep your engine running totally smoothly.
Finally, part 5, when the engine stalls, looking at common cardiovascular disorders.
So what happens when the most resilient machine ever built faces chronic stress, wear and tear, or poor maintenance? Well, it usually breaks down along the exact lines of our engine analogy. It can be a plumbing issue like hypertension overworking the pump against extreme resistance, or atherosclerosis clogging the internal pipes with plaque. If those clogged pipes happen to be the coronary arteries feeding the heart muscle itself, that leads to coronary artery disease or a myocardial infarction, what we know as a heart attack. It could also be a pump failure, like heart failure, where the left or right side of the heart simply can't squeeze hard enough anymore. Or it can be electrical glitches and mechanical door failures, causing arrhythmias and valve disorders.
From perfectly timed electrical sparks and flawless mechanical valves to pressure-regulated pipes and a wildly efficient dual-circuit pump, this system is a true marvel of nature. I really hope this explainer has left you just as fascinated by your own internal machinery as I am. So I'll leave you with this final thought. With your heart pumping 5 liters of blood a minute around the clock without you ever having to ask it to, what are you doing today to maintain the ultimate biological engine?